Hello everyone. Today we're going to talk about covariance matrices. The prerequisites for this material is some linear algebra, vectors, matrices, inner products, projections, multivariate random variables, and all the material we saw about expectation. The goal is to describe the average behavior of multivariate data using the covariance matrix. So we already learned what the mean of a scalar random variable is. Now we're going to extend that concept to data that are modeled as a random vector in d dimensions. We define the d-dimensional mean of a random vector as the vector that contains the means of each of its entries. For matrices that have random entries inside, we define the mean of the random matrix in the same way. Okay, so here we have random matrix X. We define the mean of X as the matrix that has the same dimensions as X and contains the means of each of the entries. It turns out that linearity of expectation, which we proved for random scalars, also holds for random vectors and random matrices. So for example, if we have a random vector X, we multiply it by a deterministic matrix A and we add a deterministic vector B. This is exactly the same as multiplying the matrix by the mean of the random vector. So what I mean is taking the expected value of the product plus this other vector is exactly the same as first taking the expected value of X and then multiplying by the matrix and adding the deterministic vector. So this is exactly the same as what we saw in the scalar case. Same thing for random matrices. I will have a random matrix X, we multiply it by a deterministic matrix A, and we add another deterministic matrix B. If we want to compute the expected value of that, it's exactly the same as first taking the expected value of the matrix, which remember is just taking the expected value of each of the entries, then applying the deterministic matrix, and then summing up the other deterministic matrix B. Let's prove this for the vector case. The matrix case is exactly the same. So here it's important not to get confused by all the notation and to understand what each object is at every point. So here, by this first notation, what we mean is we have a vector that is AX plus B. We take its expected value. That is just going to be another vector. Okay, and for that vector, we take a look at the ith entry. This is what this means. Okay? This is the vector, which is the expected value of AX plus B, and this is the ith entry. Okay, so by definition, the ith entry of the expected value is just the expected value of the ith entry. This is just by definition of the mean of a random vector, which we saw a moment ago. Okay? So again, the notation here is this is the ith entry of the random vector, and we're taking the expected value of that ith entry. Now, this random vector is basically computed as a matrix A. Actually, why don't I use straight lines, which would be more pleasant to the eye. So we have a matrix A times a vector X plus another vector B. Okay, and everything, let's assume everything has the right dimensions. So we're saying AX plus B. Okay, and this is the random vector AX plus B. Okay, and we're interested in an entry. So that entry is going to be a row of the matrix times X plus an entry of B, just by linear algebra. Okay, we're interested in the expected value of that entry. So we can express that entry as this row, okay, the ith row of x, each like multiplied by each of the entries of x, plus the ith entry of b. But now this is just the expected value of a linear combination of scalar quantities. So we can apply the linearity of expectation for scalar quantities. So this is just equal to that same linear combination, but now we put the expected value inside. And now essentially what we have is the ith entry of a multiplied by the mean of x, because the mean of x contains the mean of each of the entries, plus the expected value, plus the deterministic vector b, the ith entry of that. Okay. So all that this is saying is that if we define the expected value or the mean for vectors and matrices as the expected value or the mean of each of their entries, so applying just expected values entry-wise, then linearity of expectation holds for them in the sense that if we multiply them by a deterministic matrix A, and then we want to take the expected value of that, we might as well apply the deterministic matrix A to the expected value directly, okay, by this proof. This is what this is saying. When we want to estimate these means of random vectors or random matrices from actual data, what we do is very simple, because the mean of the random vector of the random matrix is just, again, the entry-wise mean. We just estimate each of these entries with the sample mean from the data. Okay. So now we will see why I started talking about linearity of expectation for random vectors and matrices, and that's because we're going to see now how to characterize the variation of multivariate data, and a pretty intuitive way of characterizing this variation is using variance. The problem is that the variance is only defined for scalars. Okay, it's unclear what the variance of a vector would be. However, if we have a vector, a natural way to quantify how it varies is to ask how different linear combinations of the vector vary. Okay? And by linear combinations, we mean taking a linear combination of the entries. So here, in this linear combination, we're weighting the ith entry of x by the ith entry of a deterministic vector v, and then we're adding them up. Okay. So now we can ask, what is the variance of this scalar quantity, which is this linear combination of the entries of x? Well, by definition of variance, it's equal to the expected value of the linear combination minus its mean. Here, we can apply just linearity of expectation to say that this is exactly the same as v transpose x minus e of x. Okay, so computing the linear combination of the centered vector. This centered vector, we're going to call it c of x to simplify notation. Okay, so we have that the variance of the linear combination is the mean square of the linear combination, the same linear combination applied to the centered vector. And now we're going to split this in this way. So just to be clear, what we're doing here is we're saying, okay, this inner product is equal to b times the centered vector, and now we can choose to write the square, okay, the square of b transpose c of x in this way. Well, sorry for my deficient drawing skills. So just to be clear, let's see. This is v transpose. This is c of x. This is c of x transpose. And this is v. Okay. So I hope it's clear that this is the inner product of these guys is V transpose C, and the inner product of these guys is also V transpose Cx, so it's exactly equal to this. Okay, so I hope that is clear. The cool thing about writing it like this is that now we have a quantity here that is a matrix that only depends on X. Okay, and as we will see, the expected value of that matrix is what we are going to define as the covariance matrix. So now, by linearity of expectation, remember this is a matrix that is the outer product of the centered random vector. If we want the expected value of this quantity inside, by linearity of expectation, in particular applied to random matrices, we have that is exactly the same as multiplying V transpose and V outside and taking the expected value of the entries of this random matrix. So now we are that is what we define as the covariance matrix of a random vector. And again, I just want to stress that the motivation for this is that we want to define an object that captures the variance of the linear combinations of any linear combination of the random vector. Okay, so this is the definition of a covariance matrix. And it turns out that we can also write the covariance matrix, and this is probably the definition that you have seen before or that you will see quite often, as variances and covariances of the entries. Why is that? Well, let's consider X, which has dimension 2 and such that the mean of X is 0, just for simplicity. Then if we compute the expected value of X transpose, which is equal to the outer product of the centered values, because we're assuming that the mean is 0, again just for simplicity, then what we have is the expected value of x1, x2 multiplied by the transposed x1, x2, which is equal to the expected value of a matrix that contains x1 squared, right? Then x1, this is just linear algebra. I'm just multiplying these two vectors. x1, x2, oops, sorry, let's see, x1, x2, and the fourth entry is just x2 squared. Okay, so you might want to verify this. And now, when we take this expected value can go inside entry-wise, because this is just a random matrix, and the expected value of this, if the mean is 0, is just the variance. So here, the expected value of this is just the covariance of x1 and x2. The expected value of this is the covariance of x1 and x2, and the expected value of this is just the variance. Okay, so this is an easy way of defining the covariance matrix. You just say that the diagonal entries are the variances, and then the off diagonals are the covariance of those entries. But it's important to remember that all of this essentially comes from here, because the covariance matrix allows us to compute the variance of any linear combination of the random vector. This is exactly the same argument as before, and at the end of the day we get that if we want the variance of a linear combination of the vector that is given by a vector v, of the random vector that is given by a vector v, then we just need to compute the quadratic form which applies v on the left and right to the covariance matrix, and that automatically gives us the variance of the linear combination. Let's see a concrete example. In this example, there's a cafe that serves their signature cheese sandwich, and this sandwich has 3 ingredients potentially: bread, local cheese, and some imported cheese. And now this random vector x captures the price of the ingredients, which may change because of the global economy or because of local conditions or who knows. And from past data, the people from this cafe have realized that this random vector has this covariance matrix. So in particular, realize that this means that the variance in the price of the bread is 1, the variance in the price of the local cheese is 1, and the variance of the price of the imported cheese is 1.2. So the imported cheese is what has more variance in its price. Something else that is important to realize is that the covariance between the bread and the local cheese is actually very high, because the bread is probably also baked locally, so maybe the local economy is very important for this, whereas the price of the imported cheese is actually completely uncorrelated with either the local cheese or the bread, because again, maybe the bread is just, probably the bread is baked locally. So now this cafe is considering two different recipes. In one, they use bread and the two kinds of cheese. In the second, they just use bread and the local cheese. So the question now is, which of these recipes have the higher standard deviation or the higher variance? So realize that if we just took into account the variances, then it looks like using the imported cheese is probably a bad idea, because it has a pretty high variance, or a higher variance than the local cheese, but that would ignore the covariance. And that is crucial, as we will see in a moment, because we're going to compute the standard deviations of these two recipes. Let's start with this one, where we have a linear combination, which is basically, if you realize, the vector 100, 50, and 50, okay, applied to x. And now, by what we have just learned, essentially the way we can compute this is by applying this vector v, okay, to the this is v transpose, to the left and to the right of the covariance matrix. That we have just learned that this automatically gives you the variance of the linear combination. We have proved, I mean. Okay, so that's exactly what we do, and we take a square root because we're interested in the standard deviation. We plug in the matrix there, and you should verify, because as you know, sometimes I make mistakes, that we get that the standard deviation in the price of the first of the sandwich according to the first recipe is 153 cents. Now we want to compare this with this other possible linear combination. This is easy to do because the covariance matrix gives you the variance of any linear combination. Okay, you just have to apply the appropriate vector on the left and the right of the covariance matrix. We again make these computations, and hopefully I didn't get anything wrong, and now the variance is 164 cents. So interestingly, just using the local cheese actually increases the variance because of the covariance, the high correlation between the bread and the local cheese. Okay, if the price of the bread goes up, then the local cheese goes up at the same time, so the price of the sandwich really goes up, whereas this wouldn't happen with the imported cheese because they are uncorrelated. It's uncorrelated with both the bread and the local cheese. So that's why we're seeing greater variance if we don't use the imported cheese. But the point here is that the covariance matrix gives you the variance of any linear combination of the random vector. If we want to estimate the sample covariance from data, essentially what we do is we build an average of these outer products, or equivalently, this is exactly equivalent to computing the standard, the sample variance and the sample covariance, and just plugging them in to each of the entries. Okay, so now let's see an example with real data. This is the position, the latitude and longitude of the most important Canadian cities. And this is the covariance matrix. So here, something to realize is that the variance in this direction is much larger than the variance in this like north-south, and also that the covariance between them is negative, essentially because of all the people living here. So if you live at a larger longitude, so towards the east, then it's more likely that, on average, that you live more towards the south, towards a smaller latitude. So that explains the negative covariance. It's always, when you see a covariance matrix, it's always good to take a little look at the different variances and covariances and see if they make sense. So now it turns out that just as in the case of the actual covariance matrix, not the sample covariance matrix, if you take a linear combination, if you consider a linear combination of the data, meaning you take a linear combination of each of these dimensional data points, and you want to consider the variance of that, it turns out that the variance of that is exactly given by a quadratic form that depends on the sample covariance matrix. And the argument to prove this is almost exactly the same as in the case of the actual covariance matrix. The reason is that the expected, so here we're taking averages, and in the case of the covariance matrix, we're taking expected values, and they're both linear. So that's why the proof is essentially the same. Okay, so this denotes the sample variance of this list of numbers that we obtain by taking the inner product of V and each of the d-dimensional data points. And by definition, this is just basically the numbers minus their sample mean, and then we're just taking an average of their squares. Again, just by definition of sample variance. And then what happens here is that we can center the numbers. Okay, this is just by linearity. Actually, I made a small mistake here. So you can show basically that V transpose mu, where mu is equal to 1 over n of xi, okay, that this is exactly the same as mu of xv, okay, where mu of xv is basically the mean of this. Why? Because mu of xv is 1 over n and this by linearity of sums is just equal to V transpose 1 over n. So again, all of these proofs are the same because the average and the expected value are both linear. Okay, so this is what I had skipped here. So essentially, again, we can remove this part, and we have that this is just equal to this, is just equal to the inner product between V and the centered vector, okay, by this argument. Okay, now annoyingly this is going to appear again, but I'm going to remove it again. And now, exactly the same as what we did for the covariance matrix, we can write V transpose Cx squared. We can just write it as V transpose Cx. There's an I here that I'm missing. Transpose V, and again you have this outer product, so this looks like an outer product like that, and now we're averaging those outer products. So this is the same as what we were doing for the actual covariance matrix. We ended up with an expected value of the outer product. Here we end up with the average of the outer products, and plugging that in, we get this average of the outer product. That this average of the outer products gives you the sample variance of any linear combination of the data. Let me erase that again. And that's what the sample covariance is actually giving you. When you compute the sample covariance like we did for the Canadian data, that will automatically give you any linear combination of the variance of any linear combination of the data points. So now let's imagine that we're interested in what is the variance of the cities, so the, like the city locations in Canada when you look at this from the southwest, so in this direction, from the southwest to the northeast. The way we're going to compute, by what we mean is basically, what if we project each of the cities onto this line? Okay, that just gives us variations in this, and here the same. So we're going to project the cities onto that line, and we're going to see the variance of their location only from the southwest to the northeast. If we do that, if we take this in our products, we end up with these data points here in this RAG plot, and here we have shown a KD, like a kernel density estimate of their density. Now what we're interested in is what is the variance of these data points, the sample variance of these data points. Well, you could just compute that sample variance, but it turns out that this is completely encoded within the sample covariance matrix, as we just proved. So in order to compute that, we just need to compute, this would be V, this would be this V transpose, this is V, and this is the covariance, the sample covariance matrix, which we should write like that. Okay, and if we compute that out, we get that the variance in that direction is 229. Again, the take-home lesson here is that the sample covariance matrix automatically gives you the sample variance in every direction of this d-dimensional space when you have d-dimensional data points. In the case of the Canadian cities, this is just equal to 2 so that we can visualize things better. Okay, so we just confirmed that indeed, if you would take the sample variance of these points, you would get 229, which is the same thing that you get from the sample covariance matrix. So basically, the sample covariance matrix gives you the sample variance in every possible direction of space. Here, this is a plot of this quadratic function, okay, which we can call g of v as a function of v. So as you move v around in this two-dimensional space, so just to be clear, let's go back to the map. So if the origin is here, I'll use another color. Let me use maybe a more prominent color, maybe this. So this is the v that we have considered, but we could consider any other possible v. And for any possible v, you're going to get a different sample variance. And this is what this function gives you, this quadratic form. Okay, this is a quadratic form where you plug in a value of v, one of these vectors, into d, and it gives you the sample variance in that direction. And this is what this function looks like. This is the particular v that we have been considering from now up until now. It's from the southwest to the northeast, and it has it has L2 norm equal to 1, which is why it's on this circle. This circle contains all the vectors that have L2 norm equal to 1, and this value here. So these contour lines are giving you the sample variance for each of those values. Okay, this would be 229. This is kind of interesting. This allows us to visualize the sample variance in every possible direction. If we restrict ourselves to be only on this circle, okay, that has radius 1, then you would get a function like that shows you how the sample variance varies in every possible direction of space. And this is interesting because you could ask, how are we going to find the maximum or the minimum? Well, this is encoded obviously in the sample covariance matrix, and as we will see in the next video, you can find those directions by applying principal component analysis. Okay, so what we have learned here is that the covariance matrix encodes the variance of any linear combination of a random vector, and also that if you consider a data set with d-dimensional data points, their sample variances, the linear combination of, the sample variance of any linear combination of those d-dimensional data points is captured by the sample covariance matrix. Thank you very much.